Suppose, for example, we were trying to calculate the average age of the entire student body of Bunker Hill Community College. That average age would be the mean of our population, or mu. Now, we may not be able to calculate mu because we would have to collect data from every single student at the college. So instead, what we would do is that we would take a sample. We may take a sample of 100 students or 200 students or maybe only 30 students, and we would compute the average age of that sample and get a sample mean, or in other words, x bar. Now, whatever we calculate for our sample mean, let's say we had a sample mean of 24, it's probably not exactly equal to the mean of the entire population, or mu. It's going to be off by some amount, and that amount that it's off by is called the margin of error. Now, we would like to get some information about the margin of error, but since we don't know mu, we don't really know how far off our sample mean actually is. But we are able to get some information about that margin of error, and we're able to establish some percentage probability with it as well. Before we do that, we need to understand what a confidence level and a critical value is. I want to consider the normal curve. If I take a look at the normal curve, I could pick out two z values on the normal curve. We'll call them negative zc and positive zc. And there would be some area under the curve in between those two z values. Basically, this blue area right here is the probability that a normally distributed variable would fall between zc and negative zc. For instance, let's consider z equal to 1.96. Remember that z values refer to how many standard deviations I am away from the mean. On the normal curve, the area between negative 1.96 and positive 1.96 is equal to 0.95. Another way to think about this is that the probability that any normally distributed variable is within 1.96 standard deviations from the mean is approximately 95%. So if you have data that's normally distributed, you can say that 95% of it will be within 1.96 standard deviations of the mean either way. Similarly, you could say that for z equal to 2.58, that 99% of the data would fall in that range. What we do with that information is that we can actually gather information about this margin of error. Now, the derivation of the formula is a little bit advanced for intro to stats, but it basically takes the formula for a z value and uses some algebra to rearrange it so that we get a probability interval for the margin of error, which would be our sample mean minus the population mean. That margin of error is based on those z critical values and also depends on the standard deviation of your data as well as the sample size. Going one step further, what we can actually do is create an equation or an interval for the population mean itself. So what happens is that I'm able to create a range of values for the population mean based solely on what our sample mean was, and also the factors of the margin of error, which include the critical values, the standard deviation, and the sample size. We will see in a few examples on how to use this formula and how the interval is created. But the main factor here is that we're considering the standard normal curve and z critical values. Now, when we create a confidence interval, we need that z critical value along with a standard deviation and a sample size. But you'll notice that this formula relies on having the population standard deviation, sigma. That's actually pretty rare to have. It wouldn't make much sense to know what the population standard deviation was if I didn't even know what the population mean was to start. So what generally happens when I'm creating confidence intervals is that I end up using the standard deviation of my sample as opposed to the one from the actual population, which I don't even know the mean of. When I use the standard deviation of a sample, what happens is that I no longer use a z-value or a z-critical value in my formula. I use instead what's called a t-value. And a t-value is based off a different type of distribution called the student's t-distribution. The student's t-distribution is a lot like the normal curve, but the size and shape of the curve varies. The student's t-distribution is not standardized. It varies based on sample size, or more specifically something called the degrees of freedom. The degrees of freedom are equal to the sample size minus 1. We'll see how this factors into calculating our confidence intervals as we go forward. If you read in your book will tell you that you use the student's t-distribution, or t-critical values, in a confidence interval calculation if sigma is unknown. In other words, if I don't know the population standard deviation, I'm going to use the sample standard deviation instead. This all goes back to the derivation of the confidence interval formula. Again, it's not something we're going to have to replicate or something we'll get into too deeply. But if I don't know sigma, I'm not really computing a z-value. I can't really use the standard normal curve. So instead, I use the student's t-distribution.